Okay, let's take a look at the Polynomials test review. So this is our first page, which covers the first couple of topics we dealt with. Some basic up here, some terminology. If I want an example of polynomials that fit these descriptions, so quartic binomial, binomial means there would be two terms, quartic means the highest degree would be 4. So there's no shortage of examples you could have here. Very simple example might be x to the 4th plus 5 or something like that. But whole other host of examples like -3 x to the 4th, and then I could have something with an actual x over here. I could have plus 10x cubed or x squared or anything like that. So long as 4 is the highest power, that's what makes it a quartic. B asks us for a 6th-degree polynomial. Now, polynomial, I specifically mean not a monomial, binomial, or trinomial in this case. So if you say polynomial that's none of those, that means I need at least 4 terms. So I need something that's 6th degree with at least 4 terms. Now I could make this very simple or more complicated. I could have something like -2x to the 6th, and then I just need at least 3 more terms. They could be x to the 5th, x to the 4th, x cubed, and so on, so long as they're all less than x to the 6th. So I might add here, just for some randomness, plus 10x to the 5th, minus x to the 4th, and then just for kicks, I will skip down and write plus 11/2 x. Now that is a polynomial. It has 4 terms, so it's not a monomial, binomial, or trinomial, and the degree is 6 because that's the highest power. Now, let's get into this business of end behavior and what the degree tells us about the graph of the polynomial. So, right here, I'm given a graph and asked to analyze it for end behavior. So as x approaches -infinity, so this means for very, very small x's. So in other words, I'm thinking about the left side of the graph. And as x approaches +infinity, well, there I'll be thinking about the right side of the graph. As x approaches -infinity, what's happening to the y's? Well, I can see I am going up. I'm increasing, so y is going towards infinity. On the right side of the graph, well, I can see that side is also going up. So that's also infinity. Looking at this graph, I want to ask how many x-intercepts and turns do I have? Well, I can see that I have 1, 2 x-intercepts. And as far as turns, those are my relative minima and maxima. Right here, I've got a minimum, a maximum right there, and another minimum down here. So it appears that I have 3 turns. Now, we want to use this information to come up with the minimum degree of this function. So let's remind ourselves how this works. If I know that a polynomial has a certain degree, n, then that means it has at most n x-intercepts. It could have fewer. We've talked about things like multiplicity. We could have imaginary roots and so on. And it could have at most n-1 turns. Now, the trick of this is if I'm going in the opposite direction, the degree tells me the most number of x-intercepts, and degree -1 is the most number of turns. If I know the number of x-intercepts or turns, what I actually know is that the degree is at least some certain value. Because if I have 2 x-intercepts, I could have a degree 2 polynomial or a quadratic, but I could potentially have a 3rd degree polynomial or 4th or 5th or any higher degree. Similarly, if I knew the number of turns, I can predict the degree of the polynomial. So let's look at this right here again. I see that I have 2 x-intercepts and 3 turns. Well, based on the number of x-intercepts, 2 x-intercepts would imply that my degree is at least 2. 3 turns, since I know the degree has to be 1 more than the number of turns, 3 turns would suggest that my degree is at least 4. Now, if you're thinking about that, if I have one bit of information tells me the minimum degree is at least 2, and another that says the degree is at least 4, I have to go with the greater one there. If it's at least 4, it cannot be 2, or for that matter, 3. So I will ignore this. I don't need it anymore. The minimum degree is 4. And that would make sense with what we see up here. I see end behavior that suggests an even degree polynomial, And I can tell that this is not a quadratic because that's not a parabola. So thinking more specifically about end behavior, I can see here that both sides are going up. Now, while we can express this in the mathematical notation right here with infinities and negative infinities, we can also describe this verbally by saying things like the graph rises or falls on a certain side of the graph. So let's think about that. Let's think about how we might express that terminology. Here, I can say that this graph rises on the left and rises on the right. How could I apply this terminology to some other functions? Here I have f of x, which is negative 2x to the fifth plus 12x squared minus 9. So in order to describe end behavior, I know I need to look at the degree and the leading coefficient. So I'll be looking at the highest power term, which is negative 2x to the fifth. 12x squared and minus 9 are not going to influence the end behavior. So I have here an odd degree polynomial and a negative leading coefficient. So we might recall, what does this tell us? Well, again, if I have a polynomial with an odd degree, that means the ends will go in opposite directions. A polynomial with an even degree means the ends go in the same direction. If the leading coefficient is positive, the graph will go generally up, whether that's going up from left to right or both ends go up. I see here these are an example of an odd degreed polynomial and an even degreed polynomial. Now, if the leading coefficient is negative, and I put this together with what I know about odd degree and even degree polynomials, a negative leading coefficient makes the graph go generally down, whether that's again from left to right for an odd degree polynomial, or both ends going down if I have, here I have some sort of kind of funky even degreed polynomial. So I remember these things, we remember these things, what an odd degree means, an even degree, and what the sign of the leading coefficient tells us. So going back here, if my function is negative 2x to the fifth plus 12x squared minus 9, well, I have here an odd degreed polynomial because 5 is odd, and my leading coefficient is negative. So an odd degree and a negative leading coefficient tells me my ends go opposite places, and this graph goes generally down. So it does something like this. It might be a little bumpy in the middle. I don't know. But the left side is rising, and the right side is going down or falling. Looking at these descriptions right here, this fits best with B. Take a look at G right there. What should we be considering for G? Well, in G, again, we want to look at the highest power term, which is right here. So I can see that my degree for x to the 8th is even. My leading coefficient is negative 1, so that's negative. If I have an even degree polynomial, my ends will go in the same direction, and a negative leading coefficient, again, means this graph will go generally down. So what does it look like? It could be somewhat bumpy in the middle. I don't really know. But what I do know is the end behavior. Both ends are going down. Both ends are falling, which among these descriptions fits best with D. All right. The next idea we dealt with was turning points. I already mentioned turns in the previous problem number 2. If I'm looking right here, this graph was taken from Desmos. Desmos will give you all the x-intercepts, the y-intercept, and the turning points if you just plug in whatever function you might be looking for or considering. And we can give the characteristics of this graph. Now, not mentioned here is domain and range. This is going to go forever left, forever right, which means my domain would be all real numbers, negative infinity to infinity. And it will also go forever down and forever up. So my range would also be negative infinity to infinity. Up first, though, I am actually asked about the intercepts. So my x-intercepts are the points where the graph hits the x-axis. Now remember, if you're ever asked for intercepts, these are supposed to be ordered pairs. So I can say negative 2, 0. The next one is given as 0.50, which certainly you can write that, or you can write the fractional equivalent, 1/2, 0. For 4.50, again, 4.50 is fine. As a fraction, that is 9 halves. For my y-intercept, that's also given to me, right here, 0, 4.5. And again, I can write it as a decimal. I prefer fractions, so I will write it as a fraction. Just remember, intercept means you need to give me an ordered pair. If you're asked for the zeros from a graph, well, zeros relate to x-intercepts. Zeros, roots, solutions, x-intercepts, all related terms. But where intercepts must be ordered pairs, zeros are just the x values. So I would say x is equal to -2, and then I could say 0.5 and 4.5, or I could use the fractions that I previously said. Those are my zeros. Now perhaps the trickier part, the relative minimum, relative maximum, and then using these to state the intervals of increase and decrease. So, looking right here, well, I see these two turning points. The turning points for a polynomial graph are the relative minimum and relative maximum. And I could have more turns, which means I could have multiple minima or multiple maxima, entirely possible. In this case, I have one of each. Down here, this is the relative minimum. And I can tell that because if I look only nearby, this is the lowest point in some section of the graph nearby. This right here is the highest point in some section nearby, so that's a relative maximum. Remember how we describe these? Relative minimum or relative maximum is always described as the y value at whatever x value. So for my relative minimum, I can say -18.816, I'll go ahead and use all three decimals in the approximation given to us, at x equals 2.893. For the relative maximum, I look up here. X is -0.893, y is 8.316. So then for our intervals of increase and decrease, I use these. Remember to do intervals of increase and decrease. What you got to recall is you're always using x, going from left to right, and since we'll be doing these in interval notation, you really don't want to use brackets as far as we're concerned, because at these turning points, the graph isn't increasing or decreasing, it's turning. So for the interval of increase, I come in from the left and I am increasing. I increase from very, very small x's until I reach this point where x is -0.893. So my interval of increase is -∞ to -0.893. And then I'm going to start to decrease. I decrease as x goes from -0.893 until I reach my next turning point where x is 2.893. After that, I will increase some more. So to put on another interval of increase, I will put a U, which stands for union, which is what I use when I'm joining multiple intervals. And I increase as x goes from 2.893 to very, very large x's as I go to the right to infinity.